Hi there. In today's lecture, we're going to be starting a new chapter called Differential Equations. So in this lecture, we'll go through the basic types of differential equations with a few examples, and then in the next lecture, we'll go through some more difficult examples. Okay, so a differential equation is something like the following. So we have dy by dx, so the derivative of y with respect to x is equal to some function of y and x. So in this case, we call this a first order differential equation because we have a first order derivative. So this is called a first order differential equation, or DE, because we have a first order derivative. Okay, given by this dy by dx. Now what we want to do is solve for y. So we know the derivative of y, but we want to undo this derivative and get back to the original function y. So we want to undo this derivative to get back the function y. Now, in some cases, this can be very easy. In other cases, this can be quite difficult. So we'll look at the different types of functions f, and the first few will be easy, the second few will be a bit more difficult, but it's not so bad. Okay, so the different cases correspond to the different types of f that we will see. Okay, so depending on what this function looks like, we're going to have to use different methods to undo this derivative. So the first case, or the first method, is called direct integration. Okay, so this is the simplest form. So this happens when we have dy by dx is just equal to f of x. So no y dependence on that right-hand side. Okay, so we don't have any y dependence on that right-hand side. It's just some function of x. So in this case, it's very easy to solve because we can just integrate both sides. So we can have the integral dy dx is the integral f of x dx. Okay, and we know from the fundamental theorem of calculus that the integral and the derivative, they cancel each other out. So on the left-hand side, we just have y of x. On the right-hand side, we have the integral f of x dx plus some constant c. So in fact, when we undo this derivative operation, we end up with a whole family of solutions. Okay, one element of the solution set for each value of c. So each value of c gives a new solution in the solution set. Okay, often we call that the family of solutions. Okay, so we get a whole different set of solutions given this different value of c. If we want a particular solution, we can use what is called an initial condition. So to get a particular solution, this may be just a problem that's given, or it may be something based on like a physics problem. For example, if you know the velocity of a particle, you can integrate that to get the position. You use some initial condition, and then that will give you that particular solution for that situation. Okay, so to get a particular solution, we need an initial condition. Okay, so this is some initial value that we use to fix whatever that value of c would be. So at x is equal to 0, y0 is equal to y0. So we can use this bit of information to substitute it into the solution and allow us to solve for c. So we can use this information to solve for c. Okay, and then this problem of finding y becomes what is called an initial value problem. So we call this situation an initial value problem. Okay, there's quite a bit of theory behind this, but we're not going to be getting into that. We're going to be focusing more on the mechanics of the problem. So how do we solve these problems? What do the solutions look like? And where might we see these problems, in day-to-day workings? Okay, so we're not going to be focusing too much on the theory behind this. Okay, so this is the first method, direct integration. We won't be seeing this too much because it's too simple. Okay, so this is just your normal integration that you've done before. Okay, what we're going to be looking at next is called separable solution, or separable equation. Okay, so in this case, we have our dy dx, as we had before, is equal to f of x comma y. But now this is going to take another particular form. We're going to assume that we can write this right-hand side as the product of two functions. So we assume that we can write this as g of x times h of y. Okay, so this gives us a separable equation because we've separated out the x terms and the y terms into this product. So given some differential equation, if we can do this, if we can separate this out, then we can use this method to find the answer. So what we do is we separate things out. So on the right-hand side, we still have x terms and y terms being multiplied. We're going to rearrange some things to have the one side being x only and the other side being y only. So we take this dy and divide by h of y. So now that side is only y terms. And this is equal to g of x dx. And that right-hand side is only x terms. So what we can do now is integrate both sides. So integrate. Now the left-hand side, we can integrate that easily. There's nothing too difficult there. The right-hand side, we can integrate that because that's just a function of x. Again, nothing too difficult there. And then we need to add our constant c. Now we run into a problem sometimes where this left-hand side gives us a complicated function of y. This can be a complicated function of y. Okay, now if we want to solve for y, we need to find the inverse, right? We need to invert that so that we can solve for y. Sometimes we can't do that. There might not be an inverse. Sometimes there can be an inverse. So we need to look out for those particular cases. So sometimes we can't solve for y. And so we are left with an implicit equation. Implicit equation of x and y. Okay, so the equation will have x terms and y terms, but we need to keep in mind that those y terms are actually functions of x. Okay, but sometimes we can invert it, and then we can solve for y as we would normally do. Okay, so this again is what happens when we can separate that right-hand side into a product of two functions like this. Okay, so this is a separable differential equation. Okay, the last one that we're going to be looking at today is called a homogeneous differential equation. Okay, so again, we have our dy by dx is equal to f of x comma y. And again, we're going to be looking at a particular form of this. We're going to be looking at situations where we can write this right-hand side as g of y over x. Okay, so in certain situations, this right-hand side can be written like this. If that's possible, then we call this a homogeneous differential equation. Okay, so what can we do in this situation? Well, since we have this right-hand side being g of y over x as a single variable function, instead of f of x comma y, which is two variables, what we can do is make a little change of variables to simplify this. So we can set u is equal to y over x. So instead of working with two variables, we can work with a single variable function. Okay, so this will become g of u. So that's for the right-hand side, but for the left-hand side, we still need to find dy by dx. So what is this dy by dx in terms of u? Okay, so we can just start with the u function. So u is y over x. We can rearrange this to get y is equal to u times x. Now we want dy by dx, so let's take the derivative on both sides. So dy by dx is going to be du by dx times x plus u. Okay, so that's just using the product rule. So we differentiate the first one, leave the second term, so du by dx times x, plus we leave the first term and we differentiate the second. So now we've written the dy by dx in terms of u. Okay, so now we have dy by dx in terms of u. Okay, which is what we wanted to do, since this right-hand side only depends on u now. So we can substitute that in. So we're going to have du by dx times x plus u is equal to this function g, but not of y over x. Remember, we set that to be u, so that will be g of u. Okay, and we'll see that after making the substitution, this becomes a lot easier to work with. So this is easier to work with. Okay, so what we do is we solve this easier equation for u, and then we just substitute back. So we solve for u, so that's u of x, and then we substitute, so remember u is equal to y over x, so u is y over x, so that means y is u of x times x. Okay, and then this is the solution we wanted. So we wanted this y solution. Okay, and of course we can add our plus c. So we can solve for u, and then remember to put your plus c, and then we can, so solve for u plus c, so I'll just put this in quotes just so you don't forget. Don't forget the plus c. Okay, so when you solve for u, remember to put your plus c after you integrate, and then that's included in the solution. Then we can multiply by x, and that gives us our y solution back. Okay, so that is the idea behind all of these methods. Let's have a look at some examples. So we'll do an example for each. So number 1, direct integration. Okay, so let's say we have dy by dx is equal to 3x squared plus cos x minus 1. Okay, so this might come up in some situation where we're looking at the rate of change of some function y. Okay, so this is used a lot in engineering and physics and so on. Whenever we're modeling some situation, we usually model it in terms of a differential equation. Okay, so physics, chemistry, biology, a lot of those situations have these differential equations with them. Okay, so dy by dx is equal to this. We see that the right-hand side doesn't have any y terms, so we can use direct integration. So we integrate both sides. Okay, and then remember to put our plus c so we don't forget that. Okay, so again, fundamental theorem of calculus, that undoes the integration and the derivatives, so we just have y of x. And then the right-hand side, we're going to get x cubed plus sin x minus x plus c. And if we were given some initial condition, then we could then solve for c. So let's say we have the initial condition that y at pi over 2 is equal to 0. Okay, so this will be provided with the differential equation. So we can use this to then solve for c. So we have y is 0 and x is pi over 2. So we're going to have pi cubed over 8 plus sine of pi over 2, that's 1, minus x, that's going to be pi over 2. Okay, and then our plus c. Then we can just take everything over. So we get c is equal to minus pi cubed over 8 minus 1 plus pi over 2. And this is the value of the constant c. So we can take this value of c, substitute it into our solution that we found, and then that gives us our full solution to the initial value problem. Okay, let's have a look at the separable situation. So number 2, separable. Okay, so let's say we have dy by dx is equal to xy squared plus x. So here the right hand side doesn't look like it's a product of two functions. We've got xy squared plus x, so it's not a product of two functions, but what we can do is factor out the x, so we can have x y squared plus 1. Now it is a product of two functions. We've got x, that's the function of x, and y squared plus 1, that's the function of y, and it's in two parts like that. So sometimes it may not look like a product of two functions, but a bit of factoring will get us to a product of two functions. So we can use some factoring to get the product. Okay, so sometimes we need to do a little bit more work to see what type of method we need to use. Okay, so now we're going to take all the x terms to one side, the y terms to another side, and then integrate. So we're going to have dy over y squared plus 1 is equal to x dx. Okay, so that's just separating each thing to its own side. Then we can integrate, and then remember the plus c. Okay, integrating is straightforward. So we're going to have arctan of y is equal to 1/2 x squared plus c. Now, remember what I said previously, sometimes it's going to be difficult to find the inverse, so we can't solve for y. In this case, we can. It's very easy to do. We can just take the tangent on both sides. So we can have the tangent of arctan of y is equal to the tangent of 1/2 x squared plus c. Okay. Then the tangent of the arctangent, that just cancels, so we have y of x is equal to the tangent of 1/2 x squared plus c. Okay, and if we want to solve for c, we have to have the initial condition. So sometimes that will be provided, then we get one solution. If the initial condition is not provided, then we get a family of solutions. Okay, so for this one, we don't have an initial condition, so we get the family of solutions. So we get a family of solutions. Okay, and then the last one on the homogeneous case. So let's have a look at an example with that. Okay, so here we have dy by dx is equal to x plus y over x minus y. Now, this doesn't look like that case of y over x, but like the previous example, sometimes we have to do a little bit of work to get to that point. So we want y over x, but here we've got x plus y. What we can do is factor out an x at the top and at the bottom. So we have x, 1 plus y over x, and then in the bottom, x, 1 minus y over x. Okay, so we just factored out the x there. So now we can cancel out the x's, and then notice in the top and in the bottom, we have y over x in the top and y over x in the bottom. That's what we needed for this homogeneous case. So we have y over x, y over x. Okay, so what we do is we set this y over x to be u. Okay, so u is equal to y over x. We can rearrange this a bit, so y is equal to u times x. Can take the derivative, so y prime will be u prime x plus x. Plus u. So when you use the product rule, so differentiate the first one, we get u prime, leave the second x, plus we leave the first one, differentiate the second. So we end up with this as our y prime. Okay, but now in terms of this u variable. So the left-hand side we can replace with this. So we have du by dx times x plus u is equal to 1 plus u, because we made the change, and divided by 1 minus u, again with that change of variables there. Okay, so this doesn't look any easier than what we started with, but we can simplify this and we'll see that it does become easier. So, du by dx times x is equal to 1 plus u over 1 minus u minus u. Okay, now to simplify this, it would be nice to have the same denominator. So let's turn this u into u times 1 minus u over 1 minus u. Okay, so that gives us the same denominator for that. So here we have du by dx times x is equal to 1 plus u over 1 minus u. Okay, and then we have the same denominator here now, so minus u, 1 minus u. Okay, we can clean up the numerator a little bit. So we have du by dx times x. So we're going to have 1 plus u, but then a minus u, so that cancels. And then minus u times minus u, so plus u squared. So we're going to have 1 plus u squared over 1 minus u. Okay, so if you don't see what happens with that, please just expand out that bracket on the numerator, and then you'll see the terms cancelling. Okay, now this almost looks like the separable situation. So we have x by itself, we've got the u terms by itself. We can take this fraction over to the other side. We can take the x over to the other side. And then that will give us our separated equation. So taking the u terms over, we get 1 minus u over 1 plus u squared du. Taking the x over, we have 1 over x dx. Okay, so we have separated this out. So all the u stuff is on the left-hand side, all of the x stuff's on the right-hand side. We can integrate, and then remember our plus c. Integrating this, it's pretty easy to do. We can separate this into two terms first. So we have 1 over 1 plus u squared du minus integral u over 1 plus u squared. Okay, makes it a bit easier to separate it out. Is equal to integral of 1 over x. We can do that right away. That's the natural log of x plus c. Okay, then integrating the left-hand side, the integral of 1 over 1 plus u squared, that's just going to be arctan of u. This, again, quite easy. We're going to have 1/2 the natural log of 1 plus u squared, natural log of x plus c. Now we see that this left-hand side is a very complicated function of u. So we're not going to be able to solve for u. So we're going to have to leave it as an implicit equation. But the last thing that we can do is substitute back. So here, remember, u was y over x. So we can substitute that back and we can get our implicit equation. So here we have arctan of y over x minus 1/2 the natural log 1 plus y squared over x squared is equal to the natural log of x plus c. Okay, so unfortunately we can't solve for y to make it a nice equation of y equals something. So we left with this implicit equation. Yeah, but we can leave it like this. Okay, so I'll just leave you with a little bit of homework. Okay, show that the solution satisfies the original differential equation. So show that the solution satisfies the differential equation. Okay, so what we want to do is take the solution, find dy by dx, and show that we do get back to this differential equation if we substitute in. Okay, so it's not so bad. Try it out. Okay, and see, can we get back to the original differential equation? Okay, so that's going to be it for today's lecture. In the next lecture, we're going to be looking at a few more examples of each, just to show the manipulations required, some of the difficulties you might see. Okay, that will all be in the next lecture. Okay, the video should be up sometime tomorrow. Okay, also please note that since we are working online now, that the tutorials will also be online, and that will be done using the tutorial WhatsApp groups. Okay, so the same groups that you used last semester with the tutors, we're going to be using that again. Okay, but then when we go back to in-person, we will have the normal tutorials. Okay, while we're on that, please go through the tutorials. The solutions will be made available soon, but just for now, look through these different methods and see what you can do with that. Okay, so yeah, please try do them before looking at the solutions, but the solutions will be available later so that you can check your work. Okay, as always, if you have any questions, please just send me an email, or you can email the tutors for help. Okay, so the next video with more examples will be available later on, so please look out for that.